thanks everybody for coming to this meeting. It's great to see so many people from across the spectrum of our users, including the academic sector, the research laboratory people, as well as the commercial people. What I'm going to talk about today is our new performant framework that we've been developing for our vSim software, but it is so different and it has changed so much that the name is going to be changed to represent the fact that this is pretty much a completely new release of the software. It's in terms of the framework, but not in terms so much of the GUI, although we've added a few things that I'll talk about today. In particular, though, the software in terms of all the electromagnetics has been implemented on GPUs, and we are in the final throes of the software release process, which involves getting all of the examples to work, finding bugs, squashing bugs, and so on and so forth. So I'll tell you a little bit about what we've been able to achieve so far. This is the preview of this XSim 1.0. We don't have a date yet for its release, and we're always hesitant to give a date because somebody always finds one more thing to fix. But I'm anticipating a few months. So what XSim does is combining GPU and ultra high performance with the very flexible vSim physics framework. As I mentioned, it's a ground up rewrite of the physics capabilities for performance in what we call our new cross-dev computational framework. Cross-dev refers to the fact that the framework has been written in such a way that basically the same code can run across either GPUs or CPUs. And that has a big advantage because when you do it that way, when somebody comes up with a feature request, you can very quickly write something, test it on the CPU, and be fairly confident will work on the GPU. Of course, you have to test there too, but you don't have to code it twice. But while doing all of this, we're going to make sure that our software, that the same interface is provided to the user. Finally, I'll talk about the cloud capability that's coming available at about the same time as XSim, although it will be slightly earlier. And if you want, you can register for cloud access using, if you are willing to be a beta tester, and try it out on the cloud provider of your choice. Reminder about TechX. You're here, you probably know about us. We focus on plasma simulation, and historically, that was a code that was called vSim. The computational engine was known as formidable. And we provide simulation software that contains the necessary physics for simulating plasma. That is to say, charged particles interacting with external and generated electromagnetic fields. Now, electromagnetic fields is here meant to be inclusive of electrostatic and magnetostatic approximations. We have extensive collisional processes and extensive boundary processes, things like secondary emission, ionization, elastic collisions, and so on and so forth. We are trying to bring plasma modeling into the commercial world. And of course, there are a few others out there, but what that means is being able to deal with complex geometry and CAD definitions. And we focus on high performance, but flexible high performance. And what I mean by that is the software will run on anything from laptops to supercomputers. And finally, we concentrate on ease of use. We sometimes call this democratization of plasma simulation. And what that means is people can come up to speed very quickly on this code. And for me, since I'm also a professor at the University of Colorado, that's very important. I can get my graduate students on this code solving physics problems very quickly, rather than worrying about the particulars of compilers and operating systems and so forth. But in summary, then what TechX is about is the latest advances in physics research to solve complex real-world problems. XSim 1.0, what that's going to be about is fast electromagnetics. As I said, There's no release date at present. We divide up our examples into 4 electromagnetics application areas. This now I am referring to dynamical electromagnetics, not electrostatics. We do have that as well. That will come out later. But those areas are antennas, scattering, like radar cross-section calculations, cavities and waveguides, and photonics. And photonics is really taking off as an area of simulation. In order to do those things, we've had to code up our algorithms, implement algorithms both that exist out there in the wild, and as well algorithms that we ourselves have developed, published, and been actually very well cited for. And those include algorithms in FDTD. This is all FDTD, electromagnetics. Algorithms that accurately represent conformal boundary conditions for both perfectly electrically conducting shapes, PECs, and conformal dielectric shapes. In fact, our group was one of the groups that published probably what is the most accurate method of doing conformal dielectric shapes within finite difference time. In order to get those, but it's not enough to have examples and coded up algorithms. You need all of the things that surround those algorithms, and that's what we've been working on. Things that allow you to get problems set up and analysis done. Just to give you an example of some of the things that we now have working, and I think we're unique, for example, in that we have the total field scattered field box working on GPUs. I don't think anybody else has that right now on GPUs. We can do far field calculations. We have unidirectional launchers. These are all things for getting the signal into the system, into the simulation. We've got all of those working. But then you get the signal into the simulation, you do the calculation, that's the algorithms. And then finally, you have to get some data out. If you don't get data out, there was no point in doing the calculation. So we separate that into 2 parts. One part is data capture, and that's to have sensors that you can put throughout your simulation. What's the field versus time and location? What's the entire field on a slab, which is something you need, for example, to do S parameter calculations. What are the pointing fluxes? Where's your energy going? And then you have to take those histories and do data analysis on them to extract things like S parameters. And we have S parameters that allow you to, for example, in one simulation, gain the S parameters for, let's say, a splitter and photonics across both legs of the splitter, across a band of frequencies, all within one simulation. And if you used our code, you know about that. As I said, this new cross-dev framework is what we're building on, and we've implemented everything within that. It was a ground-up rewrite for performance and minimal memory usage. It has improved memory access. All the memory has been aligned such that when you do a calculation bit by bit, you bring in and stream the energy in over all of the operands that you're going to operate on in your calculations. For memory, we've improved the way it can use memory by allowing for defining fields over a subdomain. To give an example of that, if you have a large domain where you're doing a calculation, you have to put a signal and define it over some small region. You don't want to have to define an entire field for that one signal. And so now we're allowed to do things. Now we can do things over a subdomain and save all of that memory usage. Furthermore, we use separable functions for the most part to minimize evaluations at each time step. In the previous VSIM framework, we would have a function that was some arbitrary function of space and time. Now we find that most people are dealing with functions which are a function of time times a function of space. And what that allows you to do is to define the function of space over a slab where it's needed once at the beginning of the calculation. And then in every subsequent time, simply multiply that times the function of time and then add it to the field. This is, for example, for a current that's used to launch a wave into an electromagnetic simulation. And we've done all this while making the changes with XSim minimal. So let me show you the calculation. This is our XSim calculation. In this particular case, this is what we call a Y splitter. This is a photonics device, which brings in an electromagnetic wave from the left, propagates it through the simulation, and the signal is split into the two arms and it comes out on the right. And the design process for Y splitters, what you want to do is calculate this little area down in here and shape it in such a way that nothing reflects and everything goes down the two legs equally. And that is true over a range of wavelengths of light. I've already done this calculation. Actually, I'll come back and I'll show you a little bit more. What the heck? When I come back, I want to show you that in the setup, it is the same as it has been before. You can define a full set of constants. You can define parameters, which can be functions and arithmetic operators on any of the constants or of the parameters that it depends on. Cannot have circular dependencies. Otherwise, any formula will work. In the basic settings, you will now see that actually field infrastructure here actually can't be changed. In XSim, you can have any field infrastructure you like as long as it's crossed out, to use an old joke. And then you can, as before, set the default number of steps, the precision. And this is an important new thing the GPU has found. The way the new framework works is that if you have this variable true, and it finds the GPUs, it will use all the GPUs that it finds. If it doesn't find GPUs, then it uses the CPU, because then it defaults to a number of cores that it can find. But you might be on a machine where you don't want to use the GPU, say it's not a very performant GPU, then you would set that variable to false. Other than that, most things are the same. One of the nice things that Dan just told us is the MPI decomposition. And you say, oh, but there's a field everywhere. Maybe you don't need it. Actually, it is interesting. You can make a decomposition such that you put lots of cells in, say, an empty area where you don't do much complicated calculation. Actually, you wouldn't do that in this problem, but it's a possibility of doing it. You can set the field solver. This is electromagnetic. The dielectric solver, you have choices like permittivity averaging or point permittivity. Those are basically second order and first order. You can add in a plasma dielectric if you like. And this is useful for people who are doing reentry problems. But mostly what you see here is what you've seen before. You can add in materials like silica and silicon. You can add in geometries. You can define your grid. And this, by the way, we're working on to make much more easy the definition of variable grids. And then you have your fields, your field boundary conditions, which are your launchers. You can have, this is a current distribution, which launches a wave. It's actually quite cool, and I'll show you that in a minute. And then finally, histories. These are various diagnostics that you can put on the problem to calculate the power going out various parts of the simulation. So it helps you find how well you split the problem. The run is, as you've seen before, it has not changed too much, mostly incremental. But as usual, if you decide at runtime you want to take a different number of steps or a different periodicity for dumping, or you want to restart in a particular number, all of those things can be done. And in the run mode, you can set up parallel, serial, or scheduler. For example, if this thing detects a scheduler, it will try to use Slurm, and then it will work better for it. In this particular case, this is an M1 Mac. And some of you may know it has 8 kind of ordinary cores and 2 low power cores. And so typically this is best run with 8 cores. And so that's the number of processors. And then proceeding on through, one thing I believe is going to be new in this release is the scan feature, which allows you to launch a number of simulations with parameters varying over some grid, and you can just launch that, go home for the night, and then come back the next day, say, and see which one turned out best, and then proceed with that design. And analysis is before, but of course, there are fewer analyzers here. Why are there fewer analyzers? Because there's no particles in these simulations. And so you do a different sets of analyses. And finally, visualization. So for this particular simulation, it starts off quiescent. And then the first time step, there is a mode, and it's being launched here, right here at this -10 number. And this is one of the things we really like about this, is this is called a unidirectional launcher. And what that allows is you, for the largest part, to launch your simulation, electromagnetic radiation in only one direction, because the radiation that goes backwards is of no help. And in fact, it hurts you because it reflects off the boundaries of the simulation and can interfere with your signal analysis. And you see the pulse comes through, it ends into the splitter area, it splits down the two legs, and finally it goes out. The simulation, the right of the simulation, we have an absorbing layer, an adiabatic absorbing layer that allows this to go out, allows the radiation to go out. This is much better seen if you go here and you come back. Let me get rid of those triangles. They're in the steering. Back to here. You can see, if we go back to here, back when there's one signal, that the signal gets to be a maximum of about 2.5 times e to the -6. So you can change this to -2.5 e to the -6, and the maximum to 2.5 -6. And set those. And now you can actually see with a constant amplitude what your simulation radiation does. And now you can better see that it comes in and then leaves. Okay. All right. So now let's move on to the next thing. What I mean by minimal is, yeah, names are going to be changed. We're trying to come up with more consistent names across all of the different aspects of the code. And so what that means, if you had something that worked in VSIM, even though the interface is basically the same, it's going to have to be different. It's going to have to be recoded for XSim because the names have changed. The data structure, as I mentioned, was changed to get better memory performance. It's now component major, as we call it, better streaming. If you follow the visual schema, what we call VSH5 framework for importing, if you import fields and you look at them outside of VSIM, VSIM will take care of it. Use VSIM. But if you're doing it outside of VSIM with, say, NumPy and Matplotlib, you're going to have to make sure that when you were reading it, you were doing it in a way that was VSH5 compatible. Then it will work. Otherwise, it's not guaranteed. Here's some performance numbers. And this is going to give you an idea of how much performance is improved. I was just showing you the Y splitter. That's a small simulation, 2.4 million cells, 3,000 steps. And so it's saying what we call 7.1 gigacell updates are done in that simulation. On this Mac, no GPU, no Macs have GPUs, right? 8 cores, that simulation takes 2 minutes, 121 seconds. If you do the same thing, and that was the VSIM framework. If you do the same thing in the XSim framework, you get a 2.4x speed up just by using the different frame. It's that much faster. If you move it over to Linux and you have a machine with an RTX 3060, you get a 4.8 times speed up. That's a gamer G. That's not a computational G. If you now take it over to our system and you put it on an A100, you get a 20 times speed up at 1.2 gigacells per second. But if in fact you make it a much bigger problem, you take the same problem and divide, make the cells smaller so that you have 100 million cells, you now get 3.7 gigacells per second, which is 50 times faster. And if you take that same problem, and we are going to do a little bit more tuning, the best we've seen is about 6 gigacells per second. We're talking about the fact that the cross-DAP framework And compared to this Mac laptop, which is not the best comparison, you might compare it to 32 cores. But let's say at this simulation, you're going to be running 75 times faster, close to 100 times faster on a GPU than you would be on this 8-core Mac. And these Macs are actually pretty darn fast. And I think they're equivalent to a lot of x86 chips at 16 cores. It's okay, it's not 100 times faster. It's only 50 times faster. But I, I think that's, see here. Oh, it's not finishing. See here? It might not just freeze. There we go. Okay. Now, we further have it fully parallelized across all the GPUs. And that's giving one the ability to do incredible problem sizes at incredible speed. Here's an example of the speed up for a case where we're doing 64 million cells per GPU. And I'll get to performance issues a little bit later about that, where we decomp the system purely along the X direction, which is the propagation direction in the previous problem. Photonics tends to be wafers, which are thin in one direction, and they are longer or wider in the other directions. And you want to cut them so that you're cutting them along that propagation direction, or possibly that and transverse. What you don't want to do is cut them along the Z direction, which is the direction of fastest variation. But as long as you avoid that, you can see here that with 8 GPUs, we're getting about 45 gigacells per second. So now when you compare that to existing codes, let's go back here. Can't do it. Existing codes like Visa, which is 60 megacells per second, and now you're getting 40 gigacells per second. That's almost 3 orders of magnitude speed up. But of course, you have to have the GPUs, and we're going to tell you in a minute how to get those. There are a few special memory considerations with GPUs, and that is because you want to stream things in a certain way, you tend to store more things in memory, and GPUs do not like irregular access. So we actually store a few more quantities so that they can be regularly accessed. And what that ultimately means is you need about 100 bytes per cell in float precision and 200 bytes per cell in double precision. And I'll discuss the implications of that in a moment. So now let's look at the GPU that is right for you. As I said, a commodity gamer GPU generally has poor double precision performance. You're going to do float. And if you're going to do that, anytime you're going to stick with float, you're going to have to restrict yourself to explicit calculations that are not too big because you can't afford the round offers. A really good, probably the top of the line gamer GPU right now, I think, is an RTX 4090, which costs about $1,200. It has 24 gigabytes of memory. So you're going to work in float. That means, coming back to here, that you're going to do 100 bytes per cell. So if you have 24 gigabytes for memory, you can do a 240 megacell problem. And that's pretty good. So now you want to start saying, what kinds of problems am I going to do? What kind of GPUs do I want to buy? But I'm going to show you in a minute, you don't want to even do that. Computational GPUs have good double precision, and they have really good memory streaming, but their memory is still limited, at least by CPU standards. So the B100, which was the the two previous generation, had a maximum of 16 gigabytes. So you could do a maximum of 160 megacells in float and 80 megacells in double. A100 that's out now, that's what we have here, has 80 gigabytes, so you can do 800 megacells. But remember, that's per GPU. And we have parallel capabilities. Put 10 of those GPUs together, and you're now doing almost 1 billion cells per GPU. You're now doing a 2 billion cell problem. And the code scales very well. The point here is that buy your GPU, depending on what you want for performance and memory, And this is a little bit of a guide to how you want to do that. And then finally, the cross-step parallel capabilities are going to allow you to solve large problems. All right. So where do I get to? I remember going to a conference once and I'm talking to some guy and he says, all you can do is put this on 100,000 cores. And he looked at me cross-eyed and says, where do I get those 100,000 cores? Because I have it on my laptop, right? We have a new tool that's coming online and it's called XSim. And we're very thankful to many of our customers who are already starting to beta test this thing and for helping us work out some of the issues. It's basically ready, but as anything in software, there are little glitches that come along that you have to deal with. So I'm now going to take you over to CloudSim. And over here, I have the CloudSim portal. Let's see, I want to get right. How about there? So now this is the CloudSim portal. Oh, I've been inactive for 30 minutes. And I've actually just created a new compute system. And so this CloudSim is basically a front end for you to have a dashboard for dealing with your Amazon account. Now, how do you create clusters? If you've ever been through the Amazon interface, boy, that's tough. I've actually got 2 clusters going here. And so you say, how hard is it to create a cluster? I say new compute system. I want product. I want to use my key pair that I've defined here. I want to make it, and I'll call this Cary, I don't know, twist. I will choose the hardware, and I want you all to notice that I'm doing this in real time. So if there's any bugs, that won't be fun. But anyway, I'm going to choose the hardware. I'm going to say, I'm going to look for, show me all the hardware. It starts with P3 because I happen to know that those are the hardware. That's the hardware with the NVIDIA instance on them. I create it, and then I just press the button, create cluster. Now, I'm not going to do that now because it takes 5 to 10 minutes to get that done. Amazon really doesn't have a very rapid system for setting up their clusters. On the one hand, that's what you would say. On the other hand, if you're like us and you actually had to go out and buy 8 nodes with all the GPUs in them, hire somebody to wire them all together in a rack, and then get the networking correct, and then get your router correct, that's a lot more than 10 minutes. Okay. So don't think about that 10 minutes as being a big deal. Just compare it to what would happen otherwise. So now I'm going to close this because I don't want to make that. But when I have that cluster, and here I have a cluster, I can connect to the head node. And when I connect to the head node, you'll notice down here, this thing created a password for you. You will have gotten that if you sign up for it. And I can copy the password and I can connect to the head node. And all I do is say connect. I put in the password and I'm not going to do that because I already have one back here and I don't want to have 2 of them. So I'm going to cancel out that one. And I'm going to look and tell you what everybody's wanting. Okay. That's actually the portal. And then this over here, I don't know anymore. This over here is the simulation, the actual simulation that I've been doing. And in this particular simulation, my goodness, that sure looks a lot like the previous code I showed you. But it is the previous code, except now it's running in the cloud and it's running on Amazon. In the basic settings, I have the various things set up. It's the exact same thing. And I've already run this problem. It takes about, what are you doing on a GPU, 6 seconds to run. But I'm not going to bother here because here is the simulation all complete. And this was the end of the simulation. And so it tells you, it shows you the signal that's leaving the simulation. So basically, everything that I can do on my desktop, I can now do through the web, and I can do it in Amazon, or I can do it locally. Come back to that in a minute. I can do it at Amazon. And what this requires is that you have it right now. What it requires is that you have an Amazon account. And we ask you to set up a few things on your permissions. You ask your IT people to do that. You give us something. And then when you run our code, it's charged to your account. And then we actually have a licensed server that sits there and counts the clicks as you're using these XSim, excuse me. And then it basically then tells you how much you're using. And then we actually have, and I'll come back to that in a minute. But if you don't want to use Amazon, if you have your own cluster, this is the exact same thing. But this case, it's running at hydrogen.txcorp.com. Our goal here is to offer you multiple solutions for cloud computing. I see that I'm going over in time. I hope I can be spared an extra 5 minutes. There's many uses for CloudSim. You just might be saying, I want to build my own dedicated cluster. But before I do that, I want to see how the code runs on a V100, because maybe I can buy a bunch of those used. Or maybe I can buy an A100, or maybe I can just get away with compute with an ordinary CPU. We are trying to make that aware for you and work for whichever way you want to work. And in fact, we've developed a new bursty license where it just charges you according to the number of compute hours that you have used. Now, I will tell you that this is great because you don't have to go out and buy those GPUs. But I'd be telling a little bit of a fib because there's a GPU shortage going on. It's hard to get GPUs right now. And NVIDIA is making buckets of money. But that affects Amazon too. So what that means is you may not be able to create the workstation at Amazon that you want. On the other hand, you may want to go to another cloud provider. And here's where I could use some help from you folks who are on. Because we have this all working with Amazon, but maybe you use Oracle or Azure or Rescale or Google. If you use any one of those, could you be so kind as to write in the chat box which one you use so that we know where to take this thing to next? We believe and have from our market research believe that Amazon is the biggest player right now for scientific computing, but we'd like to make sure that's the case. So once again, if you could put in the chat box any cloud provider that you use, that would help us figure out where to go to next. Okay. So I guess what I want to finish off here by saying here is we have a new cross-dev framework that provides a dramatic increase in performance. What did I show? If you're looking at parallel GPUs compared to a typical 16 or 32 core CPUs, you can get to a factor of 1,000 times faster. Of course, like anything else, all it takes is money. You just got to buy those GPUs. They're expensive, but if you need it, it's been providing a dramatic increase in performance. The engine, computational setup, all the diagnostics are much faster. It automatically uses GPUs when found and uses the best CPU configuration when it is found. And these performance increases are on top of all the other performance increases you heard today. Dan Murray was talking about how you can improve performance by doing this recursive domain decomp, where you concentrate your calculation where the particles are. By the way, we don't have particles in this framework yet, but this will, when we do get particles in, these performance increases will be on top of all those other increases. So we're not just going after increasing performance by porting things to the next biggest hardware, also going after improving things by getting better algorithms and better memory access, etc. You can go to XSim. You don't really, if you're a vSim user, you don't have to learn anything new. Basic interface is unchanged, but some simplifications and variable name changes. For the most part, the data capture and analysis is available as before. Some things have been combined, moved around for efficiency. And finally, I want to say that it is now cloud available. So even if you don't have the hardware on your premises, you can do this kind of calculation with an Amazon account. And what we are finding is that our large customers, our Fortune 500 customers, are all telling us, hey, we're moving to the cloud, at least in part, and can you make your software work there for us? And we, of course, are responding to our customers. I think that's it. And I'll stop there for now, and I'm glad to answer any questions.
We have some questions up here for you.
Igor, yes, I like your question about the X platform. It might be interesting because Elon Musk likes to make everything X, space X, and so on and so forth. That we could now go to and get some funding for our next development. I'm actually not sure that computational physics is one of his areas of interest, but if this would help, of course, we would do it. What is the ideal strategy to solve the ES on the GPU? You'll notice I didn't present that today. We do have electrostatics being solved on the GPU. And what we are doing is simply, for us, we're doing call outs to the Trilinos library to do. We don't actually have a project in place to do ES in particular with shapes right now. We have a first solver, but we're actually doing implicit electromagnetics on the GPU. And I think it's going to be a little while before I can answer how to do that in a way that's maximally performant.
Andrew raised his hand earlier. I wasn't sure he still had a question.
Andre, did you have another question?
Oh, no, it was by mistake. Sorry. Yeah, thank you.
Well, I want to say one more thing, if I may, in response to Igor's comment or question. It's our expectation that the rate of solving in terms of the number of iterations will be the same whether one is doing something on the CPU or GPU, because they're both calling out to the same library and the same algorithms are being used. We are seeing convergence of both the implicit solver that Eve talked about, as well as the Poisson solver that we've had in place for some time. And this is a solver, by the way, that includes shapes. Okay, so you modify the electrostatic to have conformal boundaries. And we're seeing 7 to 8 iterations to solution. Eve, is that about right? It's about right. So I don't expect the number of iterations to change. And we're going to pursue that, I'll say, because that allows us not to have as much data movement between CPU and GPU. Now, there's a fair amount of question as to whether what's the actual best way, because maybe that doesn't cost you very much, but that's the way we're proceeding. Oh, what was Igor's question? Igor's question is, his serious question was, what is the ideal strategy to solve electrostatics on the GPU? And Andre, you have experience with our code, and so I think you probably have seen that I hope that we generally converge on electrostatics with using multi-grid of order 8 to 10 iterations. And so we expect that to be about the same with our Trilinos GPU. The real question is whether the GPU framework has all of its internal communications as fast as you need. All right, so yes, thanks.
Yeah. All right. Thank you all for attending, and we'll see you guys tomorrow.